Hello, and welcome to today's video on geometric sequences. This video has 5 main objectives. First, students will be able to define and recognize a geometric sequence. Second, students will be able to write a recursive formula for a geometric sequence, as well as be able to write an explicit formula for a geometric sequence. Additionally, students will be able to find any term in a geometric sequence. And finally, students will be able to determine if a given value is a term in a geometric sequence. Geometric sequences. A geometric sequence is a sequence whereby a fixed amount, in other words, a constant value, called the common ratio, is multiplied by each term to get from one term to the next. The common ratio is represented as R and may be negative or fractional. In this box, you can see the recursive formula. A sub n plus 1 equals a sub n times r. What it's saying, in essence, is that if you took the nth term and multiplied by r, it would take you to the next term in line, which would be the n plus first term. If we look at the example 2, 6, 18, 54, 162, etc., the first term, denoted a sub 1, is 2, and r is 3 since we're multiplying by 3 to get from one term to the next. In the second example, a sub 1 is still 2, but this time you can clearly see that we're multiplying by negative 4 instead of positive 3. So our value of r is changed to negative 4, since 2 times negative 4 is negative 8, negative 8 times negative 4 is 32, and so on. Imagine if each term of a sequence lined up on a number line. So they take their respective places. A sub 1 furthest to the left, a sub 6 furthest to the right. How would we find the next term? Well, if it's a geometric sequence, then we could take a sub 1 and multiply by r to get to the second term. In other words, a sub 2 would be a sub 1 times r. If we again multiply by r, that would now take us to a sub 3. So a sub 3 is a sub 1 multiplied by a pair of r's. In other words, a sub 3 would equal a sub 1 times r squared. If we multiply by r again, this time a sub 4 would be a sub 1 times r to the third power, and so on. A sub 5 would be a sub 1 times r to the fourth, a sub 6 would be a sub 1 times r to the fifth, and generally speaking, a sub n would equal a sub 1 times r to the n minus first power. You'll want to write that formula down, box it in, put stars around it because it's going to be an important formula for geometric sequences. It's given to you on the reference sheet of the Regents exam. But you'll notice when we use a sub 1 as the coefficient for r, then the exponent on r is always 1 less than the subscript of the term that we're finding. Take a look at the example, the sequence 4, 12, 36, etc. We have 5 things to do. A, explain why this is a geometric sequence. B, write a recursive formula for this sequence. C, write an explicit or non-recursive formula for this sequence. D, find the value of the 10th term of the sequence. And E, which term is 708,588? Or, if it's not a term of the sequence, which 2 terms does it lie between? For part A, explain why this is a geometric sequence. We'll take a good look at the sequence, 4, 12, 36. How are we getting from one term to the next? What is the pattern? Well, there are several different ways to go from 4 to 12. One option could be that we added 8, which would make it an arithmetic sequence. But if we apply that same principle from the second term to the third term, if we again added 8, 12 plus 8 is 20, not 36. That rules out arithmetic. On the other hand, it could be that we multiplied 4 by 3 to get 12. And if we try that same pattern, 12 times 3 is 36. So therefore, this is geometric because we're multiplying by a constant or a fixed amount, in this case 3. So my written explanation is this. This sequence is a geometric sequence because we are multiplying each term by 3 in order to get to the next term. In other words, the common ratio between the terms is 3. If I took any term and divide it by its predecessor, like 36 divided by 12 is 3, or 12 divided by 4, also 3. It's the same ratio. It's a common ratio. B, write a recursive formula for this sequence. Well, we already know to get from one term to the next, we need to multiply by 3. So if I wanted the n plus first term, I'd take the nth term and multiply by 3. But there are lots of sequences that would use the same formula. To make it the one that specifically starts at 4 and moves on to 12, then 36, what we need to do is identify at least one term of this sequence. It's most common to give the first term. That's most convenient. So by saying a sub 1 equals 4, we now have specified this exact sequence. The first term has to be 4, and then to get to the next term we need to multiply by 3. The second term would be 12, the third term would be 36, and so on. But now we're asked to write an explicit or non-recursive formula for this sequence. Well, here is the formula that had stars around it. A sub n equals a sub 1 times r to the n minus first power. And if I simply substituted my values for a sub 1 and r, I'm done. The explicit formula is a sub n equals 4 times 3 to the n minus first power. This formula is so much better than the recursive formula because if I wanted, say, the 20th term, I could just let n equal 20. A sub 20 would equal 4 times 3 to the 19th power. I wouldn't have to find all the terms that led up to the 20th power like the recursive formula would require me to do. In the recursive formula, to get the 20th term, you'd need to know the 19th term so that you could multiply it by 3. Since you wouldn't know the 19th term, pretty soon you end up back at the beginning of the sequence. Let's do just that. In part D, let's find the value of the 10th term of this sequence. Well, from part C, we found the formula to be a sub n equals 4 times 3 to the n minus first power. If I substitute 10 in for n, a sub 10 would equal 4 times 3 to the 10 minus 1 power. Simplifying my exponent, a sub 10 is 4 times 3 to the 9th power. And then asking my calculator for the value of 4 times 3 to the 9th, I find that a sub 10 is 78,732. Now, there's another way to do the same thing. We could take a calculator, and we could take 4 times 3 to get 12, the second term, and again multiply by 3 to get 36, the third term, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, and now finally the 10th term of the sequence. You'll notice that it matches what we found before. The disadvantage of this is you have to count very accurately. And secondly, if you needed to find a term much beyond the 10th term, think how long you would be repeating this procedure. In half-lives, you might have to do it thousands of times, which of course wouldn't be practical. The last part of this question was to determine if 708,588 is a term of the sequence, or if it isn't, which two terms does it lie between. Again, bringing up my formula from part C, a sub n equals 4 times 3 to the n minus first power. And now I'm substituting 708,588 in for all of a sub n. It's not the subscript. I'm asked which term, so I'm looking for the subscript. I'm looking for the value of n. In other words, 708,588 is the value of the entire term. It's not the subscript. So I would divide both sides by 4 as my first step. And now I'm at a little bit of a crossroads. I have 3 to an unknown exponent equals 177,147. Trial and error, that could take a while. But fortunately, when we don't know what the exponent is, we could log both sides. And by using the power rule, I'm allowed to bring the n minus 1, which was the exponent, out in front of the log 3. Now I could simply divide off the log of 3 and then add 1. We ultimately get n to equal 12. So therefore, a sub 12 is 708,588. Or in other words, therefore 708,588 is the 12th term of the sequence. Little different example. This time our sequence goes 6, 8.4, 11.76, and we're asked to find the common ratio. In other words, 6 times what value equals 8.4? Well, we could use division to determine that. So to get the value of r, take any term and divide it by its predecessor. 8.4 divided by 6 is 1.4. As a check, 6 times 1.4 is 8.4. In other words, the value of a sub 1 times r gives me a sub 2. However, we could have used a sub 3 and a sub 2 instead. If I took a sub 3, which is 11.76, and divide by a sub 2, which is 8.4, I once again get 1.4. And as a check, a sub 2, 8.4, times r, which is 1.4, would indeed give me the value of a sub 3, 11.76. So the conclusion, the common ratio is 1.4 in that sequence. In our final example, we have a geometric sequence with a sub 1 equaling 25 and a sub 5 equal to 60,025. And we're once again asked to find the value of r. Starting with the formula that had the stars around it, a sub n equals a sub 1 times r to the n minus first power, I'm going to let n equal 5, because that will tie the two givens that I was dealt at the start of this problem together. A sub 5 would equal a sub 1 times r to the fourth power. Now I could substitute in 60,025 for a sub 5 and 25 for a sub 1. And then I could divide each side by 25 to get r to the fourth equals 2,401. This time I don't need logarithms because I do know the exponent's value. It's the base that I don't know. So I have two options. Either I could fourth root both sides, or I could raise each side to the 1/4 power. I prefer typing into my calculator to the 1/4 power. It's just a little faster. However, the catch here is since we're doing the fourth root, we have to make sure that we remember the plus or minus that goes in front of this. And you don't do that with odd roots, but you do it with any even root. So the value of r could either be 7 or -7. Both options are valid. Take a look below. If r is 7, we'll get the sequence on the left. A sub 1 is 25, and if I multiply that by 7, I get 175. Multiplying by 7 again, I'll get 1225. Then 8575, and the fifth term would be 60,025 as required by the given. However, if you look to the right, when r is -7, and if a sub 1 is still positive 25, then when I multiply 25 by -7, I get -175. Multiplying by -7 again gives me positive 1225, then -8575, then positive 60,025. So my fifth term is still positive 60,025 as required by the givens. Values of r, either 7 or -7, are valid. I'm Murray Wright, and once again, thanks for watching my video.